Welcome. Today we will be discussing section 5.1. Topics include complex numbers, arithmetic formulas, fundamental theorem of algebra, as well as the complete factorization theorem. For complex numbers, they're written typically with a z, which stands for a plus bi, where a and b are real numbers and I is imaginary number or complex number. So we have I being equal to the square root of -1, and we have A and B being real numbers. And so some interesting properties occur with this. So for one thing, if we take a look at I equaling square root of -1, we have I squared being square root of -1 squared, which is -1. If we have I cubed, then we can think of this as square root -1 cubed, or we can think of this as I squared times I. In either case, we can simplify it to -I. And if we have I to the fourth, we then have 1, because we'll have I squared times I squared, which is -1 times -1, which is 1. Now, if I have an I to the fifth, I could reduce it down to I, because I can have I to the fourth times I to the fourth is 1, and so we're back to I. And this cycle will repeat. Now, for real numbers, what we can do is if we had like 2 plus 0i, this would take the place of real number 2 in this complex domain with the numbers. And this is just stand-in for any real number, and the only 0 that we have is if we have both 0 for A and 0 for B. So 0 plus 2i isn't 0, it's 2i. It's still a number, it's a non-zero number. That'll become important when we divide. So how do we compute these numbers? So let's take a look at z1 plus z2, and I'm going to rewrite z1 as a1 plus b1 times I. I'm going to rewrite z2 as a2 plus b2 times I. And I will always refer to them this way. So if you see an a1 plus b1i, think of that as z1. So now I can just take my real part and add it to my other real part, and we'll write this as a1 plus a2. And I'm going to take my imaginary part, add it to my imaginary part, which then I'll get b1 plus b2, but that quantity has an I, because I can distribute an I to those to make it b1i plus b2i. And we can do the exact same with subtraction. If we have z1 minus z2, we'll have a1 plus b1i minus a2 plus b2i. And that's our quantity, so we have to distribute the negative and then combine all the real parts and the imaginary parts to get a1 minus a2. And we're going to add the quantity of b1 minus b2 all of that is times by I. And so then for Z1 times Z2, for this one, we're going to write it as two binomials. So we have A1 plus B1I times A2 plus B2I. And so if I wrote this with A1 plus B1x and A2 plus B2x, we would just use FOIL, or as I prefer, double distributive, and we would get the result of A1 times A2 plus A1 B2 I plus B2 A1 I plus B1 B2 I squared. Well, we can simplify that, and we'll get A1 times A2. And if I take a look at this B1 times B2, it's times by an I squared. As we said before, I squared is just -1. So that's like subtracting B1, B2. So it's a real number because there's no more I. So we have minus B1, B2, and that is the real portion of this product. Now I'm going to gather up my i's. I'm going to factor my I out, and I'm left with A1, B2 plus A2, B1 times I. Mess this up. This is B1. This is B2 or A2. And if you notice, I just switched this A and 2. Multiplication is still commutative. And we have made a template for how to multiply, even though that you can rediscover this with just thinking this is binomial. This is especially important when it comes to the division algorithm. There is a set way. If you memorize it, that's great. However, I implore you to know how to do that, how we got to that spot, because I think that is much more applicable to basic understanding of complex numbers. So I've been referring to these things as real parts, imaginary parts, and we have to have a way of describing that, of writing that down. So if I have z being equal to a plus bi, I could have the real part, re, of z, that will be just a. I'm referring to anything that doesn't have an I attached to it. And when I want to refer to the imaginary part of z, I'm going to write that as b. So anything that does have an I attached to it. Now note, I'm not writing I here because it's assumed that there's an I there. So if I was to times b by I would get I squared, which then would make negative b. And so now the negative b would be in the real world, or the real numbers. So we can also think about is that we don't have to keep track of the number of i's, because if we have I squared, we're now real. If we have I cubed, we can just write that as the negative value of what imaginary we have times I. And then if we have I to the fourth, we're real again, and I to the fifth, it cycles through again. So remember that if real of z is anything that doesn't have an I attached to it, imaginary of z is anything that does have an I attached to it. So there are some interesting things that we can talk about with imaginary numbers. One of them being what a conjugate is. And the other one being a modulus. So for a conjugate, what we have is z bar, which is a minus bi. In other words, I'm taking the complex number and only the imaginary part, I'm attaching a negative to it. Now, the reason you might have heard conjugate before is because if I had x plus 3, the conjugate to x plus 3 is x minus 3, because when I times by these, middle terms will cancel out. Another area of math that you might have heard this is if I have like the square root of 6 plus the square root of 2, the conjugate of this is square root of 6 minus square root of 2. Because when I multiply these out, I'll get 6 squared, which is just, or square root 6 squared, which is 6, plus, or sorry, minus a square root 2 squared, which is just 2. So I end up getting 4. Now, the middle terms will cancel out because I'll get a negative square root 12 and I'll get a positive square root 12, and those two will annihilate each other, leaving us with just non-square root terms. So in a similar fashion, the conjugate of z bar will leave us with a non-complex term when times by z. And we'll see that in a minute. But for right now, we can write this as z times z bar is equal to a squared minus b squared I squared. Well, I squared is -1, so we can just drop that into the other negative to make it a positive. And so we get z times z bar is equal to a squared plus b squared. Now, for the modulus, we have the modulus of z being equal to the square root of a squared plus b squared. Essentially, it's the complex version of the quadratic formula, or sorry, Pythagorean identity. It looks like I could have like z squared equals a squared plus b squared, but I'm taking the modulus, which is similar to like the absolute value, but not really. Well, if I rewrote this as the modulus of z squared is equal to a squared plus b squared, I have a squared plus b squared, a plus a squared plus b squared. And so we can write that the modulus of z squared is equal to z times z bar, and vice versa. Z times z bar is equal to modulus of z squared. So this leads into division. Now, for division, we have z2, or let's do z1 divided by z2. And let's write out this and apply the very familiar concept of like rationalizing the denominator. So we'll have a1 plus b1i over a2 plus b2i. We want to times by the conjugate of the denominator. So we're going to times by a minus or A2 minus B2I, and times by the top, A2 minus B2I. Now we apply the bottom and we have Z times Z bar. We've worked that out and we have A squared plus B squared. So the bottom is going to be A2 squared plus B2 squared. The top, we have to work this out and we get A1 times A2 minus A1 B2I plus A2 B1I. And now we're going to have a minus, so B1 times negative B2, but we're going to have I squared, so we're going to have positive B1 B2. So let's group all of the terms together, and we end up getting A1, A2 plus B1, B2, and I'm going to split this fraction. So I'm going to divide this by A squared plus, or A2 squared plus B2 squared. And that's going to be my real part. Now I'm going to add my imaginary part. So I'm going to have negative A1 B2 plus A2 B1 all over A2 squared plus B2 squared times by I on the outside. And there we have our real part and our imaginary part for Z1 divided by Z2. Now, as I said before, you can memorize this, or you can memorize the process and replicate it when we do our work. So, the one thing to note with the division is that Z2 cannot equal 0. So let me write that here. Note that Z2 cannot equal 0. And what I mean by that is that Z2 cannot equal 0 plus 0i. If it's 2i, if it's 2, that's okay. It doesn't matter if one of the A2 or B2 equaling 0. It matters that if both of them equal 0, then Z is equal to 0. And we still cannot divide by 0, even with complex numbers. So let's see an example. So let's take 3 minus what we want to do is times by the conjugate. So we're going to have 1 minus a negative. So this is going to be positive 3i. And we're going to have 1 plus 3i in the numerator. So now when we do the top, we can distribute and we'll have 3 plus 9i minus 4i minus 12i squared. Remember that the I squared is -1, so this becomes positive 12. We're going to divide this. We can either do the formula of just 1 squared plus 3 squared, or we can work this out. Regardless, we'll get 10. And now when we simplify, we get, right over here, we'll get 15 plus 5i all over 10, which then 15 divided by 10 reduces to 3 divided by 2, plus 5 divided by 10 is 1/2. Attach the I, and there's our answer. So now that we're able to work with complex numbers, we'll now introduce the fundamental theorem of algebra. And what it states is any polynomial with complex coefficients has at least one complex solution or one complex zero. So in other words, P of x equals 0 has one solution. At least one solution. And that's when one of the coefficients of this polynomial is a complex number. So an example of this with where we can take this from kind of like a real world example is when we have P of x equals 4x squared plus 4x plus 5. And we're going to set this equal to 0. When we put this through the quadratic formula, we get x is equal to -4 plus or minus the square root of 4 squared minus 4 times a, which is 4, times c, which is 5, all over 2a, which would be 8. And when we do this calculation, we'll get x is equal to -4 plus or minus, and here we will have 16 minus 80, which would get -64, so we'd have 8i. We have -64, so let me write this as square root -64 all over 8, which then this is 8i. And so we get -1/2 plus or minus I, because 8 divided by 8. So where before we would have seen this negative and go, oh, there's no solution for the real numbers, but the complex numbers, we can now say, hey, there is a complex solution here. X is equal to -1/2 plus I, or x is equal to -1/2 minus I. And we can write this polynomial in the form of a factored form. So we get P of x is equal to, and we'll have 4 times x minus our solutions, so -1/2 plus I times x minus -1/2 minus I. And when we simplify it, we have P of x is equal to 4 times, we'll have x plus 1/2 minus I, and x plus 1/2 plus I. And so we could rewrite this polynomial in terms of I. So the thing to note is that the quadratic formula doesn't always help. It applies when we would normally get no solution, or when we would get no solution for real equations. But in general, we would want to focus on the discriminant. And when this is less than 0, we know that we have complex solutions. And the discriminant is b squared minus 4ac. That's inside of the square root. So whenever that's less than 0, we know that we have a complex solutions. Okay, so let's get an example of where we have to solve a complex function. So we have x squared minus 2x plus 4 plus 4i equals 0. So in this case, we have a complex value in our function. We want to solve it when this equals 0, so we're going to start with the discriminant. So we're going to have d equaling b squared minus 4ac. And we're going to find what d is. And so I'm going to take my b, which is -2 squared. So that's -2 squared minus 4. A is 1, and c would be our entirety of our constant. So we're going to have 4 plus 4i. Now, when we take this, we get d equaling 4 minus 16 minus 16i, which simplifies to d being equal to 12, or -12 minus 16i. And what we want to do is find what value do we get that makes this but squared. So we're going to have delta squared, and we're going to set this equal to -12 minus 16 squared, or 16i, sorry. We want to find such number where delta is a complex number. So we're going to have, let's do, we already used a, so let's do u plus vi is equal to delta. We're going to square that, which gets us u squared minus v squared. That's going to be our real part, plus 2uv This is going to be our imaginary part. And this is equal to negative 12 minus 16i. So now we have two equations. We have u squared minus v squared is equal to negative 12. And we have 2uv is equal to negative 16. Again, I'm focusing that this expression here, this coefficient will have to be equal to the coefficient of this I. So that's why the i's are omitted. So we can just solve one in terms of the other. So let's do u is equal to, divide by 2, so we get negative 8 divided by v. We can substitute that into the other equation, and we get negative 8 divided by v squared minus v squared is equal to negative 12. So solving for v, we'll have 64 over v squared minus v squared is equal to negative 12. Let's take 12, put it to the other side. So we're going to get positive 12 and put 0. Let's times by v squared. So we get 64 minus v to the fourth plus 12v squared is equal to 0. And now we want to try and factor this. Well, let's times by negative 1. So we're going to get v to the fourth minus 12v squared minus 64 is equal to 0. So 64 is the same as 8 times 8, but it's also 16 times 4. So if we have 16, negative 16 plus 4, that gives us negative 12. So we now have v squared. And let's do minus 16 times v squared plus 4 is equal to 0. We can split this fraction or split this factor and get v plus 4, v minus 4 times v squared plus 4 is equal to 0. So now this gets us v is equal to 4, negative 4. And then here, if we set v squared plus 4 equals 0, that will get us v squared equals negative 4. So that is positive 2i or negative 2i. So we only need one of these solutions. So use one of these v's. So for simplicity, let's select v equals 4. And we'll see why here in a second. So we plug in 4, plug it into here. U is equal to negative 2. This is paired with v equaling 4. So what this does is when we plug this into the delta, we now have that our delta is equal to negative 2 plus 4i. And This is now our discriminant. So when I try to solve for this complex equation, we will still be able to use that. Let's erase this. We'll still use the quadratic formula in the sense that we have x is equal to negative b plus or minus, and we found delta squared, which is essentially what the whole square root of b squared minus 4ac is. So we're going to just put delta here all over 2a. Well, what's our b? Our b is 2, our a is 1. We found our delta, so we're going to have 2 plus or minus negative 2 plus 4i all over, and now we plug in 1 for a, so we're going to put a 2 here. Let's divide, so we have x is equal to 1 plus or minus negative 1 plus 2i. So let's separate this out so we can clearly see it. X is equal to 1 plus negative 1 plus 2i. So x is equal to 2i. Or we have x is equal to 1 minus negative 1 minus 2i. So then x is equal to 2 minus 2i. And those are our solutions. So we're still using quadratic formula. Note that if we had a real solution, we would just attach a plus 0i. So as a small example, if we had something that looked like this, let's say it was x squared minus 9 equaling 0. We have x is equal to 3 plus 0i, or 3 minus 0, or negative 3 plus 0i. So either way, that's still a complex number. Just it's a real number written in complex form. Now, the reason why that we could have just chose any v is that we just wanted to satisfy these two equations. If I chose any other one, it would work out as you would go through and plug into your u, and you would get a respective u. And even if you had a combination of i's, the important thing is that you just can't select 0, because we had the one instance where we had negative 8 divided by v. And so we can't have v being 0. So anyways, the important step here is that this little delta is the square root of the discriminant, which is the square root of b squared minus 4ac. So it's the same thing, just new notation, further math behind it. Okay. And with that, that completes all the material for this video. For your check on learning, it will be to go through the steps of the division. So I want you to start with Z1 divided by Z2 and work through, show all your steps and get to this final step of the division algorithm. I think it's very important to start working with the conjugates, start playing around with how you add, subtract, divide, multiply with complex numbers. So basically reproduce this board's work for Z1 divided by Z2. Okay. Thank you for watching and have a great day.